All right. Welcome back to the show. This is Cubical, your favorite Cubical set seminar, and today we have a pleasure of having Ben Doherty from the University of Western Ontario, who will speak about cubical models of infinity one categories.
Okay. Thanks a lot for inviting me to be here. Good afternoon, everybody. Today I'll be discussing cubical models of infinity one categories. That is a couple of model structures on cubical sets and marked cubical sets which present the theory of infinity one categories. I should say before I begin, everything I'll be discussing today is based on joint work with Chris Kapulkin, Zachary Lindsay, and Christian Sattler. Right, so our goal then is to develop a cubical analog of the Joyal model structure, a model structure on cubical sets which will present the theory of infinity one categories. So we've got it formatted as this table here, which also appears in our paper. So for simplicial sets, we've got the Quillen model structure, and then there's the Grothendieck model structure on cubical sets, which also presents the theory of infinity groupoids, and there are a lot of natural analogies between those two. So we would like to develop a model structure on cubical sets, which would be similar to the Joyal model structure and Quillen equivalent to it in the same way. The Grothendieck model structure is analogous to the Quillen model structure. Preliminary thing that I should establish before I get into the actual content of the talk is for this work, we're working specifically with cubical sets that have faces, degeneracies, and max connections in the box category, and no other structure maps. So we don't have min connections, we don't have diagonals or symmetries or reversals or anything else, just this particular choice of maps. And we are going to be writing the cubical structure maps on the right when we apply them to a cube in some cubical set. So the I epsilon face of a cube X will be denoted X di I epsilon. And the reason we do that is for consistency with thinking of cubes as maps out of the representables and applying a structure map as precomposition. So this is our main theorem, which I'll be building up towards over the course of the next couple of hours. So we have this model structure on the category of cubical sets in which the cofibrations are monomorphisms, and the fibrant objects are a natural analog of quasi-categories in that they have fillers for what we call inner open boxes. So that, of course, raises the question, what is an inner open box? So that's kind of a subtle definition, which I'll get to later in the talk, and we'll see why that is a natural concept to define in this context. And not only do we have this model structure, but we can show that it is Quillen equivalent to the Joyal model structure on simplicial sets via the triangulation functor, much as the Grothendieck model structure is equivalent to the Quillen model structure via triangulation. So I'll start with just a little bit of review of the Grothendieck model structure so that we can kind of see how it's analogous to the Quillen model structure and get a feel for the kinds of concepts that will come up at different points later on in the talk. So in the Grothendieck model structure, as we recall, the cofibrations are the monomorphisms. The fibrations are defined by having the right lifting property with respect to open box inclusions, much as in Quillen model structure, they're defined by lifting against horn inclusions. And the weak equivalences we can characterize as being the maps that induce bijections by precomposition on homotopy classes of maps into fibrant cubical sets. Where homotopy classes here are defined in terms of the geometric product, defined by taking the geometric product with box 1, the natural interval object for that model structure. So what happens there essentially is that open box fillings sort of play the role of horn fillings in the Quillen model structure. So we'll want some kind of similar construction that'll be analogous to inner horn fillings for our cubical Joyal model structure. And we have this theorem, which is, I believe, due to Szynski, which states that the triangulation functor and its right adjoint form a Quillen equivalence between the Grothendieck model structure on cubical sets and the Quillen model structure on simplicial sets. And so that shows us then that this Grothendieck model structure presents the theory of infinity groupoids. So we'll kind of use this general overview as our guide in developing a model structure on cubical sets, which will present the theory of infinity one categories. And we'll see many things that are analogous to these basic facts about the Grothendieck model structure, which I've just described. But before we construct our model structure on cubical sets, we're actually going to begin with a model structure on marked cubical sets, which will be analogous to the familiar marked model structure on marked simplicial sets. And things will work the same way there. So we'll actually end up with two cubical models of infinity one categories, one having to do with marked cubical sets and another just for cubical sets. Right, so to properly define what marked cubical sets are, we'll go through the construction of structurally marked cubical sets. These are going to be presheaves on a certain category that we'll define. So we define this new category, box lower sharp, by adding a new object to the box category that indexes cubical sets. So we call this new object 1 subscript e, and we add a couple of new generating maps to this category. So we have a map phi. It goes from 1, so the object 1 in the box category to 1e. And then we have a map zeta from 1e to 0. And we impose the identity on these that phi followed by zeta is the degeneracy sigma 1, the unique map in the box category from 1 to 0. So we refer to presheaves on this new category, box lower sharp, as structurally marked cubical sets. And the way we think of these things is we think of them as cubical sets with markings on some of their edges, possibly multiple markings on the same edge. So the idea is that, so we refer to the representable object as we refer to the representable presheaf at this new object, 1 sub e, as box 1 sharp, and the value of a given presheaf, a given structurally marked cubical set at 1 sub e, we think of as the set of markings in that structurally marked cubical set, the set of markings on its edges. And right, and so these two new maps in box 1 sharp give us structure maps of structurally marked cubical sets. So what phi does is, if you have a given marking, a given element of x sub e, then you can apply phi to that to get an edge of x, which we think of as the underlying edge of that marking, the edge which it's a marking on. And zeta gives us a map that takes a vertex of a structurally marked cubical set and gives us a marking. So it goes from x0 to xe. And that identity which we imposed, that phi followed by zeta, is the degeneracy sigma 1. That tells you that this distinguished marking that we get from any vertex is a marking on its degenerate edge. So every degenerate edge in particular has this one distinguished marking. So now a marked cubical set is a structurally marked cubical set where each edge has at most one marking. So a marking on an edge is unique if it exists. And so in that way, being a marked edge is just a property of an edge rather than a structure that we impose on it. An edge can't be marked in multiple ways. So let C set prime denote the category of marked cubical sets, just the full subcategory on these objects. And then we can think of maps in this category as maps between cubical sets that preserve marked edges. And the idea is that when we think of these marked cubical sets as infinity one categories, we'll want to be thinking of the marked edges as equivalences. Those are the edges we want to think of as equivalences in the infinity one categorical sense. Right, so let's talk about some basic facts about marked cubical sets. A lot of these pretty much just work the same way as with marked simplicial sets. So there are two sort of obvious ways of getting a marking on an arbitrary cubical set X. There's the maximal marking, which we denote by X sharp. That's where we just mark all the edges of our cubical set. And then there's the minimal marking that we denote by X flat, where we only mark the degenerate edges. So these constructions both give us functors from cubical sets to marked cubical sets or to structurally marked cubical sets. And we have a pair of adjunctions. So the minimal marking is left adjoint to the forgetful functor from marked cubical sets to cubical sets. And the maximal marking is right adjoint to the forgetful functor. So now, in the same way as we have the geometric product of cubical sets, we also have a geometric product of structurally marked cubical sets. So to define this, we take the geometric product. Well, first we take the monoidal product on the box category and extend that to box lower sharp to get a map into C set double prime. So what we need to do then is just define what the monoidal product of this new object, 1e, will be with all the objects in the box category, in box lower sharp, I mean. So to define 1 to the n tensor 1 sub e, we take the underlying cubical set of that to be box n plus 1, representable at n plus 1, the standard n plus 1 cube. And the marked edges of that we take to be those that go from 0 to 1 in the last coordinate, with all the other coordinates fixed. So we just have a unique marking on each of those edges. And we define 1 sub e tensor 1 to the n in a similar way. Again, box n plus 1 will be the underlying cubical set of this marked cubical set that we'll get. But this time we take the marked edges to be those that go from 0 to 1 in the first coordinate. And then finally we need to define 1 sub e tensor 1 sub e, and that we take to be the maximal marking of box 2. So the standard 2 cube with all of its edges marked. So to see what these things look like, put an example up here of 1 tensor 1 sub e. So you can see this is just the 2 cube, but with the marked edges being those which, excuse me, which go from 0 to 1 in the second component, which I've drawn upward in this drawing. And so then, in the same way that we construct the geometric product of cubical sets, we can just take a left Kahn extension of this to get a monoidal product on structurally marked cubical sets. And then when we take the restriction of that thing to marked cubical sets, we'll get a monoidal product on that category as well. Okay, so as we usually see in these cases, for any given cubical set X, the functor, where we just take the geometric product on the left with this particular structurally marked cubical set, has a right adjoint, which we denote by hom r. I have to specify that this is the right tensoring functor because, of course, the geometric product is not symmetric. Right, so the n cubes and markings in this are basically what we would expect them to be. So the n cubes of hom r from x to y are just maps from X tensor box n to y, and the markings on edges of this structurally marked cubical set are given by maps from X tensor box 1 sharp to y. This is probably a good time to mention that box 1 sharp, which we defined to be the representable cubical set at this new object 1 sub E, is also the maximal marking of box 1, so that notation is consistent. And as I said, because the geometric product is not symmetric, we have a distinct functor that tensors on the right with a fixed cubical set, and that also has a right adjoint, which we call Hom left.
Sorry, let me, can I make sure I'm thinking about the
Yes.
failure symmetry correctly? Is this a feature of the cube category that you've chosen? So what I could imagine is that if, I mean, certainly it's a different cubical set if you tensor edge with a marked edge with an unmarked edge on either side. If you had a larger category of cubical sets, you might have a map of two cubes that would, sort of send the one to the other, but you don't have it here. Is that the correct idea?
That is the correct idea. It's because we've taken a very restrictive choice of the maps in the box category. So like if you took, for instance, the full subcategory of cat on those on the posets 1 to the n, then the geometric product would be symmetric and would coincide, I think, with the Cartesian product in that case. So yes, this is a feature of our choice of the box category.
Great, thanks.
Right. So then our first goal here is
Sorry, can I just add one other thing? Since we're talking about the full subcategory, to me, it's not even entirely clear what does it mean to be the degeneracy when we talk about the full subcategory. I don't think it's actually very easy to say that. And so then when we're talking about the degeneracies necessarily being marked, I'm not even sure how to define marked cubical sets in the case of maybe at level 1 is clear, but if you want the markings further, yeah. Okay, sorry, Al.
Right. The question is whether a connection should be marked or not, essentially, as a 2 cube. That's what you're getting at. I mean, don't you? What's the issue that's different from an issue you have here? Because you do have the max connections.
No, so here connections can be marked, but I think once you're in this full subcategory, then you start seeing very weird degeneracies. Like I can't quite think of an example on the spot, but I remember drawing some pictures, and I at least had trouble defining what a degeneracy is at some point, and I'm not sure if I have a specific issue, but I think it goes beyond just connections and degeneracies for markings.
Okay. Maybe a good thing to mention at this point is that we only have markings on the edges here, and connections in this setting are necessarily at least of dimension 2. Like we can't take a connection on a vertex to get an edge. That would only be a degeneracy. So connections. So connections and markings. Anyway, connections being 2 cubes or higher would not be marked. Right. So the first goal that we have here is to develop a model structure on C set prime on the marked cubical sets, which will be analogous to the usual model structure on marked simplicial sets. So in order to do this, we'll define a class of generating anodyne maps and an appropriate concept of homotopy for these objects. Right, so to define our generating anodyne maps, meaning the maps which our fibrant objects will be characterized by having the right lifting property against, well, we'll want to have some kind of maps that will ensure that these fibrant objects have some concept of composition. And we would expect these to be some kinds of open box fillings, much as inner horn fillings give us composition in quasi-categories. So the open box fillings that we use for this are those in which certain specific edges are marked, which we call the edges. contrast the pictures that we've got here, if you look at any one of these pictures, you see there are there's a pair of black edges, which we'd like to think of as a composable pair. And then there's the remaining edge, which is indicated in red, is marked, so that's something we're thinking of as an equivalence. So for any one of these open boxes, we would like to be able to construct a filler for that in some cubical quasi-category, some fibrant object of this model structure, whatever those turn out to be. And then the new edge in that filler would be something that would compose with that marked edge to give a composite of the two unmarked edges. So we have a rigorous definition of these critical edges for any n-dimensional box. Excuse me. So we define the critical edge of box n with respect to a particular face, the I epsilon face. We define that to be the unique edge which is adjacent to that face, and which, together with that face, contains both the initial vertex and the terminal vertex of the cube. So if you look at all these pictures, you can see that that's what's going on here. If you look at the red edge and the missing face in all of these, you can see that they are adjacent, and together they contain both of those vertices. Right, and so we define then the concept of a special open box inclusion. So for the special open box, the underlying cubical set map of this inclusion is just the open box inclusion, the I epsilon open box into standard n cube. And the critical edge with respect to the I epsilon face is marked in both the domain and codomain of this map wherever it appears. So for instance, a one-dimensional open box is just an endpoint inclusion into the marked interval, because the critical edge of box 1 with respect to either face is just the unique non-degenerate edge. And the two-dimensional special open boxes are exactly what we saw on the previous slide. So here, for instance, we're missing the 2, 0 face, and so the critical edge is the one that goes from 0 to 1 in the last coordinate. Right, so the second of our generating, or I guess the next of our generating anodynes is what we call the saturation map. So we define this cubical set that we call K. It's sort of the analog of the familiar interval object from the Joyal model structure. So you see we've got this middle edge here and these other two edges with two cubes, which sort of witness those other two edges as a left and a right inverse for the middle edge. And so an edge which factors through the inclusion of this middle edge into K is what we call an equivalence. So it basically just means something that has a left and a right inverse in that cubical set. And now we have a marked cubical set that we call K prime, which is where we take this K and then mark the middle edge. And then the saturation map is just the inclusion of K into K prime. So the idea is that having the right lifting property against the saturation map means that any equivalence in a given cubical, marked cubical set is marked. And then we have the 3 out of 4 maps, which I won't spend too much time on, but basically these are the inclusions of the 2 cube with 3 out of its 4 edges marked into the maximal marking of the 2 cube. So where we've got all 4 edges marked, so naturally we have 4 of these, one for each of the sides of the 2 cube. So then we define the anodyne maps to be the saturation of the special open box inclusions, the saturation map, and the 3 out of 4 maps. And then the naive fibrations are the maps having the right lifting property with respect to the anodyne maps. And a marked cubical quasi-category we define to be the marked cubical sets such that the map into the terminal object is a naive fibration, so has the right lifting property with respect to these classes of maps. And to show that something is a marked cubical quasi-category, it actually suffices just to check that it has the right lifting property against the special open box inclusions and the saturation map. The 3 out of 4 maps follow from that. Right, so one proposition that we can prove about these marked cubical quasi-categories, which kind of justifies our thinking that the marked edges correspond to equivalences, is that in such a marked cubical set, the marked edges are exactly the maps which are equivalences in the sense of factoring through K. So how can we show that? Well, just by definition of a marked cubical quasi-category, it will have the right lifting property against the inclusion of K into K prime, so that shows every equivalence is a marked edge. Now to show that every marked edge is an equivalence, meaning factoring through K, we can show that they have the right lifting property against the inclusion of that marked middle edge into K prime. And we can see that from the fact that this map is a push out of special open box fillings. So here I've drawn box 1 sharp with some degenerate edges indicated to form special open boxes. And then we can fill these special open boxes to construct K prime, that K with the middle edge marked. Right, and so now in the Grothendieck model structure, we defined homotopy in a way that involves taking the geometric product with the standard 1 cube. Now the appropriate notion of homotopy for this model structure on marked cubical sets involves taking the geometric product with the maximal marking of the standard 1 cube with box 1 sharp. So we can define an elementary right homotopy of maps from X to Y. That's a map from X tensor box 1 sharp to Y that restricts to each of these 2 maps at the endpoints. And then we can define a right homotopy to be just a zigzag of these elementary right homotopies, basically just taking this elementary homotopy relation and extending to the smallest equivalence relation containing it. And then under the adjunction between tensoring with a fixed cubical set and the right hom, these right homotopies will correspond to zigzags of marked edges in hom R from X to Y.
Sorry, I have a quick question. Are you calling it a right homotopy because you mean right, or because it looks like a left homotopy or something? Maybe, but I don't know the structure yet. So.
Oh, right. So the
right homotopy and the.
Yeah, so this is a left homotopy in the sense that it's defined using a cylinder object rather than a path object. That's a very good catch. It is right homotopy in the sense that here we tensor on the right with, okay, with the interval. Yeah. So a left homotopy would mean tensoring on the left with that interval. And we need to make the distinction again because we don't have symmetry of this geometric product.
Okay, thanks.
Oh, that was a very good point to raise.
Okay, just because I can't resist asking, are left and right homotopies both left homotopies for the model structure you're about to build?
They are both defined using cylinder objects, yeah. Right, so then our theorem that we have that this all builds up to is that there is a model structure on the category of marked cubical sets, C set prime, in which the cofibrations are monomorphisms. The fibrant objects are these marked cubical quasi-categories, and the fibrations between fibrant objects are naive fibrations. So again, that's all very similar to what we see in the Joyal model structure. And the weak equivalences, we can characterize weak equivalences as being maps which induce bijections on homotopy classes of maps by precomposition of maps, on homotopy classes of maps into fibrant objects, meaning marked cubical quasi-categories. So we may notice at this point, this looks a lot like a Szyczynski model structure on a free-sheaf category, but but it's not. So we can't construct this using like Szyczynski's general theory of model structures on free-sheaf categories, because C-set prime is not a free-sheaf category. C-set double prime is, but then C-set prime is just a subcategory of that. There is a general theory due to Olschak, which could be used to construct a model structure like this for this case. But what we did in the paper instead was we directly constructed this using Jeff Smith's theorem, because in doing that construction, that allowed us to learn more about the specific maps involved in this model structure. Yeah, so this is about the halfway point of my talk, but it seems I've been going faster than expected. I'm only 35 minutes in. Should I keep going for now and break off at a more convenient time later?
I think you can. Yeah, you can keep going.
All right.
If you have the energy to do that, then
I feel ready.
Okay. Well, if you feel ready, then who am I to stop you?
Okay.
So, and just in case, you're 32 minutes in because we started 5 past. So.
So we did.
Maybe let's reevaluate in 10 minutes or 15 minutes.
Okay.
Maybe I'll interrupt you then. And yeah, but for now, the stage and the moment are all yours, as Simon Cowell loves to say.
Okay. Maybe this
is a good time for a question.
Yes, it is. It is a very good time for a question.
Any time is good for a question.
Fair enough. Is there a model structure on structural cubical sets, a Szyczynski model structure on those that's equivalent to this?
There is, and we describe that in our paper, actually. And it's, in fact, equivalent to the model structure that we have here on marked cubical sets. It's very similar, and in fact, the generating anodyne maps are actually the same maps as we use for, for marked cubical sets here.
I also had another question from earlier. It's probably obvious if I thought about it, but you said the geometric tensor product of the structurally marked cubical sets, you say it just like literally restricts to the subcategories of those with at most one marking per edge, right? You don't have to like reflect it back or whatever.
Yeah, it does just restrict to that. So if you take the geometric product of 2 structurally marked cubical sets that just have 1 marking per edge at most, then the geometric product will also have only 1 marking per edge. In the paper, we have a fairly elaborate, or detailed, I should say, characterization of the geometric product, which makes that fairly clear. Any further questions? All right, well, how about if we move on to some new and exciting adventures?
Let's move on to adventures, yes.
Okay, right. So now, what we're going to do now is use this model structure on marked cubical sets to get a model structure on structurally marked cubical sets. So we have a result of, there's a result of Hess, Kaczorek, Riehl, and Shipley, which allows us to transfer model structures along adjunctions in very general settings. So we can apply this result to the adjunction between cubical sets and marked cubical sets, in which the left adjoint is the minimal marking functor, and the right adjoint is the forgetful functor that just takes a marked cubical set and removes the markings. So applying this result, we obtain a model structure on C-set prime, which we call the cubical Joyal model structure. So here the cofibrations and the weak equivalences are both created by the minimal marking functor. They're just exactly things that are sent to the corresponding classes in C-set prime by that functor.
Sorry, is the prime there? We obtained the cubical Joyal model structure on C-set, right?
Yeah, sorry, that was just a really bad typo that I somehow didn't catch. We get a cubical, the cubical Joyal model structure is a model structure on cubical sets. not on marked cubical sets. Yeah, sorry, that was just a typo. Right, and so the first theorem that we have about this is that a junction is actually equivalent equivalence. And that's fairly easy to see. So by definition, the left adjoint both preserves and reflects weak equivalences. So in particular, that shows that this is equivalent adjunction. And then because it both preserves and reflects weak equivalences, we can just check that the co-unit of this adjunction is a weak equivalence on any fibrant object, any marked cubical quasi-category in this case. And that follows from the fact, which was previously discussed, that in a marked cubical quasi-category, the marked edges are exactly the equivalences. So the co-unit is, we think of that as the inclusion, where we just remove all the markings from a marked cubical set, and then we have an inclusion from that into the original thing that we started with. So to put all the markings back on, in a sense, we just take push-outs with respect to the saturation map. So we'd like to analyze this model structure on C set, not C set prime. It's written correctly in this slide. So first of all, what we can say is that the cofibrations are monomorphisms. That's fairly easy to see just from the definition. It's pretty clear that a map of cubical sets is a monomorphism if and only if its minimal marking is a monomorphism of marked cubical sets. We would also like to characterize the weak equivalences, the fibrant objects, and the fibrations between fibrant objects in this model structure. And we'd like to show that it is equivalent to the Joyal model structure. So we do all of those things in the paper, and we'll be discussing those today. I wonder if this would be a good time to pause.
If you feel like it, I guess we can pause for a bit. So maybe I'll say this. Let's thank Brandon for part one, for all you know so far. Thanks a lot. And okay, and maybe I'll open the floor to questions. We had some really good questions before, but yeah, if there are any other questions, it'd be great. A lot of things that are confusing here, I guess, like symmetry and non-symmetry. So if there's any need, yeah.
So I have a question.
Okay. Oh, great.
So the ordinary box category that you're using is somehow monoidal, but of course, once you add in this extra object, it doesn't seem to be. Do you know what happens if you sort of close it up under some kind of tensor product? This is vague, but.
So I'm not sure what would happen off the top of my head. I suspect, I mean, I'm just speculating at this point. I think you would end up getting objects that would, well, that would sort of, like the representables on them would correspond to like the standard cubes with different markings on particular edges that would be given by, like, you know, the order of the monoidal factors, which ones are marked edges and which ones are cubes that you already had. But that's not something we've looked into at this point.
So it would be like if you, yeah, like the example you had, I guess, where you had the tensor of the two things together. You got the delta 2 or box 2 natural or whatever.
Yeah, I think that's what you would get. Yeah, it was just box 2 with the edges in a particular direction marked. Yeah.
So I was going to ask this at the end. But this actually feels like a good time now.
Oh, sure.
Cube categories with additional markings have come up. Do you think it might be possible to model infinity n categories using marked cubical sets where higher dimensional cubes are marked in addition to the edges?
Yeah, I'm not sure. That's an interesting idea. Again, not something we've really looked into at this point, but it may be worth looking into in the future.
Come to the talk on Friday.
Oh, is that Yuki's talk?
Yeah, Yuki will talk exactly about.
Wonderful.
I have a question. Could you comment on where connections have been used so far? It seemed to me that they were used in the definition of the interval object K.
Right. So K, the definition of K doesn't involve connections.
Okay.
Maybe I could scroll back a bit to find a picture of K somewhere. Okay. So this is K prime. Now, so these might look like connections in that they've got two degenerate edges. The two cubes here.
Oh, right, but they're pointing in opposite direction.
That's the thing. So this isn't a connection. This is two things composing to an identity. So the place where connections start to play a key role is in the comparison of the model structure that we get on cubical sets with the Joyal model structure on simplicial sets. One of the functors that we're going to be using in that comparison requires connections in order to define it.
Okay.
Right, so that's the Q functor from Monday, maybe.
Yes, it's the straightening over the point functor that you discussed on Monday.
Right.
And I know if one should talk about how the sausage was made, but I think for when we were at the level of constructing model structures before comparing them with Joyal, I think the idea was to do the whole thing in a kind of cube, like a specific category agnostic version, so that you would allow for one connection, both connections, and minimal cube category, just to have enough readiness in some sense. And then we somehow realized that there's one category that we really need to do the comparison. So then we kind of settled on that rather than, But you can, I think, carry out most, if not all, of these constructions also for the minimal cube category, which is based on the degeneracies. Unless, Brandon, you remember a specific point where... I don't know, Brandon, if you remember a specific point where we needed the connection in the construction, like in the first.
In the construction, in the first, right? So just constructing the model structures. Yeah, I don't think we really did. At least I don't recall anything. Because I mean, there may have been some stuff in defining the homotopy category where we may have used connections to construct certain three-dimensional boxes that we wanted to fill.
Ah, yeah. So my conjecture would be that it's probably still possible without connections. It's just going to be more complicated.
I would suspect so as well.
But by more complicated, do you mean? So first of all, you have a model category structure, but it may or may not be equivalent to the Joyal one, but you think it probably is, but it's not public proof. Is that a correct assessment of your position? Because I was going to ask, do you think it is?
Yeah, that's what I'm thinking. So I probably, if I were forced to conjecture something, I would conjecture that it is equivalent to the Joyal model structure. It's just somehow the comparison functor between the minimal model structure on cubicles, like minimal cubical sets, and the Joyal model structure would proceed by really adding connections and then using straightening.
I see. Thanks.
Mm-hmm.
Quick question, just to
Yes.
make sure I'm not missing something here. So if we're
Oh, yeah.
talking about having a Joyal-like model structure on
Mm-hmm.
cubical sets without connections, I believe I read somewhere, and I can try to find a citation for this, but I believe I read somewhere that the minimal model structure on cubical sets, the minimal Szynski model structure on cubical sets without connections is the Grothendieck one. And I would imagine that a Joyal type model structure would be weaker than that, which would seem to be a contradiction.
I can
Yes.
address it, or go ahead. Yeah, sorry. No, go ahead if you want.
Yeah, I was just going to say that is true, that if you run Szynski's argument with like taking the empty set as the set that you use as input to construct your generating anodyne maps, you do get the Grothendieck model structure. And I think we've even got some discussion of that early on in the paper. So that would seem to present a potential issue with constructing something like this, just using Szynski's machinery. Chris, maybe you have something you wanted to add to that?
Oh, so when you have connections, then the same problem appears, right? But there is no contradiction here, because note that we didn't use Szynski's machinery to construct this model structure. We used Szynski, you can say we used Szynski algebra. We used Jeff Smith, but Szynski algebra is essentially doing Jeff Smith, right, just abstractly. So we use Jeff Smith to construct a model structure on marked cubical sets, and then we transfer it. So we're never obtaining a model structure on cubical sets by using Szynski machinery. And in fact, the model structure that we're constructing is not an example of Szynski model structure, of applying Szynski machinery. So like it's like I think it's a like when you first see it, you can ask this question, like, why couldn't you just like say CIS 06 in brackets and do that? No, you cannot. Like, if you take the most minimalistic version, you're going to get Grothendieck, and we kind of go around during this through this marked detour in order to avoid this problem.
So are the cofibrations in this cubical Joyal model structure on cubical sets not precisely the monomorphisms?
They are.
They are.
But wouldn't that make it a Szynski model structure? It's a model structure on a pre-sheaf category which has cofibrations, the monomorphisms, and is, I don't know, combinatorial, cofibrantly generated.
Okay, so it's not obtained through the usual machinery.
Well, it's not, but it could be, since every such model structure on a pre-sheaf category can be. I'm not.
Yeah. So, I mean, one thing is when we say that that the minimal Szynski model structure on cubical sets is in the thing that we get by taking the empty set as input to create the generating cofibrations, is the Grothendieck model structure. That's what we get when we use tensoring with box 1 as the interval or as the cylinder functor. So I'm not 100% sure about this, but I wonder if using tensoring with K as a cylinder functor and these generating anodynes as the generating anodynes, we might get this model structure of Szynski's construction. Do you know if there's anything that would go wrong if we tried to do that?
But anyway, I think this just goes to show that this Grothendieck model structure on cubical sets isn't the minimal Szynski model structure.
I mean, it's minimal for that particular cylinder.
That particular choice of interval, but there are other choices of interval where it isn't. We could say the same with simplicial sets. If we started with the interval delta 1 and put in the empty set as generating anodynes, we'd get the Kahn-Quillen model structure. But that, of course, isn't the minimal Szynski model structure on simplicial sets. And it's the same situation here for cubical sets.
Okay, yeah.
Is this cubical Joyal model structure going to be monoidal?
Yes, it is monoidal, and we have a proof of that in the paper. The monoidality of it, well, we actually can show that even the marked cubical model structure is monoidal, and then the monoidality of the one of the cubical Joyal model structure follows from that, and from the minimal marking being a monoidal functor.
Right. Okay.
Mm-hmm.
Yeah, any further questions? Okay, no questions. Unless there are questions. So far, yeah. We're doing great. Yeah. Now we're actually
I'm good to
51 minutes. So how about we take a 5-minute break and then resume?
That sounds good. That sounds good.
Yeah. Oh.
Okay.
All right, folks. We're still here with Brandon Doherty speaking about the cubical models. In the moment are all yours.
All right. Thank you very much. So, as I said, we've got this cubical Joyal model structure on. Oh, I went back a bit there, didn't I? Right. So we're trying to analyze this cubical model structure on C-set. So we're going to characterize the weak equivalences, the fibrant objects, and the fibrations between fibrant objects. And we're going to show that this is Quillen equivalent to the Joyal model structure on simplicial sets. So once again, we'll need to define our generating anodyne maps. And so we're going to, in this case, we'll need to determine what the cubical analogs of inner horns are going to be. We're going to need to come up with some kind of special open box fillings that we can characterize the fibrant objects by lifting against. So now we define what we call the inner open box, the I epsilon inner open box of a given dimension n. And so this is a certain quotient of the I epsilon open box. So what we do there is we take the critical edge and quotient that edge to a point. So we just collapse that down to a degenerate edge. And then in order to define what these inner open boxes are actually being included into, we have to define what we call the I epsilon inner cube, which is just the corresponding quotient of box n. So again, that critical edge with respect to that face is quotiented down to a degenerate edge. And so we have this inclusion of the inner open box into the inner cube. So then a cubical quasi-category we define to be a cubical set such that the map to the terminal object has the right lifting property against these inner open box inclusions. And so to see why this is kind of the right notion to be thinking of here, we can observe that we can compose edges in these cubical quasi-categories. So if we have a pair of edges, say f from x to y and g from y to z, as we see in this diagram, then we can fill this out to an inner open box in x using a degenerate edge at z in this particular case. That gives us a 2, 0 inner open box in x. And then we can take a filler of that to get, in particular, a composite edge from x to z, and then there would, of course, be a 2 cube filling in the interior of this that would actually witness that as a composite of these two edges. So now we do still have a concept of a special open box in a cubical set, much like how there's a concept of a special horn in simplicial sets. So this is an open box in a cubical set X for which the critical edge is an equivalence, meaning it factors through K. And much like how quasi-categories in the Joyal model structure on simplicial sets have fillers for special horns, cubical quasi-categories have fillers for special open boxes. That's proven in the paper using a combinatorial argument. And so, as we might expect based on the name, we can show that the fibrant objects in C set, in this particular, in the cubical Joyal model structure, are exactly the cubical quasi-categories. So for a sort of brief sketch of how that works, well, every fibrant object is a cubical quasi-category because the inner horn inclusions are trivial cofibrations. So we can think about the minimal markings of those inner horn inclusions, and those will be pushouts of, inner horn inclusion. That's a typo. That should be inner open box inclusion. I caught most of the typos in this talk ahead of time, but it seems there were some left. So the inner open box inclusions are trivial cofibrations because when you take the minimal markings, you'll get pushouts of special open box inclusions in marked cubical sets. And if you have any cubical quasi-category, you can construct a marked cubical quasi-category which will have that cubical quasi-category that you started with as its underlying cubical set. To do that, you just mark exactly the equivalences in the cubical set. I have a similar proof that characterizes the fibrations between fibrant objects. So you can show that those are the maps between fibrant objects which have the right lifting property against inner open box inclusions and also the inclusions of the endpoints into K. So this is exactly what you would expect based on the analogy with the Joyal model structure on simplicial sets, I mean. And as we've seen in previous cases, we can define an appropriate concept of homotopy in this model structure. So here we would use K as a cylinder object rather than the marked interval because these are cubical sets, not marked cubical sets. And again, we have to distinguish right homotopy from left homotopy, left and right being used here in the sense of tensoring on the left or on the right because of the non-symmetry of the geometric product. So I won't go into too much detail on that. It's just the same kind of thing we've already seen. But we can characterize the weak equivalences in the way you would expect. So a map from X to Y is a weak equivalence in this model structure on cubical sets if and only if it induces a bijection on homotopy classes of maps into any cubical quasi-category. And so, so one of the nice things about this model structure is that we have a very natural and symmetric construction of the mapping spaces in a cubical quasi-category. So this is the analog of the left and right mapping spaces in a quasi-category in the Joyal model structure, but here we just have one canonical definition of a mapping space, not these two separate ones. So for two zero cubes, say x0 and x1 in X, some cubical quasi-category, we can define map x0 to x1 to be this cubical set whose n cubes are n plus 1 cubes of x, whose n plus 1 faces are the degeneracies, the degenerate cubes of the appropriate dimension at these vertices x0 and x1. And then the cubical operations, just the structure maps, the way they're computed, just come from the corresponding operations in X. So like the I epsilon face of one of these cubes in map x0, x1 is just the I epsilon face of the corresponding cube in X. So I've drawn an example here so that you can see like what a natural kind of definition this is. So a zero cube in this mapping space from x0 to x1 is just a 1 cube, just an edge of x that starts at x0 and ends at x1. So we can see we have a couple of those there, f and g, in the drawing. And a 1 cube would be a 2 cube in x. Say a 1 cube, like from f to g here, would be a 2 cube in x that has just the degeneracies at these vertices as 2 of its faces, and then f and g at the other 2 faces. So kind of just by looking at it, you can see that this is natural to think of as an edge from f to g, if f and g are vertices of this mapping space. So there's this proposition that we prove in the paper, again, perfectly analogous to the corresponding result about the left and right mapping spaces in a simplicial set, which says that if you have a cubical quasi-category and 2 vertices in it, the mapping space from x0 to x1 will be a cubical Kahn complex. And we currently are working on a proof of an analog of the fundamental theorem of infinity 1 categories for this cubical setting. So we hope to, we expect to be able to show that a map between cubical quasi-categories is a weak equivalence if and only if it induces an equivalence on the homotopy categories, which I haven't talked about today, but they're discussed in the paper. And if the induced maps between the cubical mapping spaces that we get here are all weak equivalences in the Grothendieck model structure. We have an approach for that which we expect will work out. We're just sorting out the last few details of it now. So that doesn't appear in the version of the paper that's currently on the archive. Oh, sorry, I hit the wrong button there. Right. So the last main chunk of the talk that I'll be, I don't know how I was going to end that sentence. The last main topic that I will discuss here is the comparison between this model structure on cubical sets and the Joyal model structure on simplicial sets. So what we're going to show is that triangulation gives us a Quillen equivalence between the cubical Joyal model structure and the Joyal model structure. The proof of that requires some work. So the first thing we show then is that triangulation gives us a Quillen adjunction between these model structures, and that is not too hard to do. So it's easy to show that triangulation preserves cofibrations. That's been shown in many other contexts, that it preserves monomorphisms. So we can get that just by, it's a left adjoint, so it suffices to just check it on the generating cofibrations, the boundary inclusions, to show that they get some cofibrations. And to do that, we can decompose any boundary inclusion as a push-out product of lower dimensional boundary inclusions. Push-out product, I mean, with respect to the geometric product. And by doing that, we essentially reduce the problem to showing that triangulation sends a one-dimensional boundary filling to a monomorphism, and that is clear. To show that, so then we'd want to show that the right adjoint preserves fibrations between fibrant objects, or equivalently that triangulation sends the generating anodyne maps to trivial cofibrations. So to show that triangulation will send the inclusion of an endpoint into K to a trivial cofibration, we can just directly compute the triangulation of K. It's just a two-dimensional thing. It's not hard to compute its triangulation, and we can show that that is contractible in the Joyal model structure. And then we want to show that triangulation sends the inner open box inclusions to trivial cofibrations. And that is a little bit more involved, but once again, we take the open box inclusion, and we can decompose that into a push-out product of boundary inclusions and an endpoint inclusion. So triangulation will send that to a push-out product of a monomorphism with an endpoint inclusion. And then we can use the boundary inclusions in simplicial sets, like the fact that those are the generating cofibrations there, to reduce this essentially to a problem of filling a certain open prism in simplicial sets, so a certain push-out product of a boundary inclusion with an endpoint inclusion, and you can just show that what we get decomposes. There can be a series of fillings of inner and special horns. Yeah, so anyway, that's probably enough detail about that. So the thing about triangulation, though, yeah.
I've just forgotten. Is triangulation a monoidal functor, or what does it do to this geometric product? Does it send it to Cartesian?
Yes, that's exactly it. It sends it to the Cartesian product in simplicial sets.
Okay, thank you.
So that's the key result that's being used there. Right, but so now it would be kind of difficult to just directly show that triangulation is equivalence, because it would be a bit hard to work with its unit or co-unit. So our approach then is we develop another adjunction between simplicial sets and cubical sets, and we'll show that that is equivalence, and that the derived functors then of the left adjoints are actually inverses as equivalences of categories. So we're going to start by introducing these functors Q and its right adjoint integral. We're going to start by showing that these are equivalences, and then use that to show the same for triangulation. So we have seen Q before. In Chris's talk on Monday, it was mentioned as the straightening over the point functor. But in this paper, we're going to, in the paper, we develop it using a theory that we develop of cones in cubical sets. So I'll explain what that means. So there's a family of cubical sets that we call the standard MN cones for M and N greater than or equal to 0. And what we think of these, we think of the MN cone as a cone that we get by starting with an M cube and then taking cones on it n times. So CM0 we define to be just the standard M cube, box M. And then once we've defined CMN minus 1, so this is an inductive definition, once we've got that, we define CMN using this push-out construction. So we take the geometric product of 1 tensor CMN minus 1, and we take the push-out, the inclusion of the 1, 1 face into that with the map from CMN minus 1 to the terminal object, box 0. So what we think of this as doing is basically taking a cylinder on the N minus 1 cone and then collapsing one of its faces down to a point, the same way we would define cones in many other contexts. And so by analyzing the details of this push-out construction, we can obtain a description of the standard MN cone as a quotient of the M plus N cube. So that's kind of an abstract perspective on these cones. So now we can take a look at some illustrations of some of these cones to get a better feel for what these are and what they would look like. So the 0, 0 cone is just a vertex, right? You take a 0 cube, you take 0 cones on it, and it's still just a vertex. So now C01, the standard 0, 1 cone, is just an edge. It's just a 1 cube. So this is actually isomorphic to C10. And in general, C0n will be isomorphic to C1n minus 1. And the reason for that ultimately just comes from the fact that that a 1 cube is a cone on a 0 cube. Here's a more interesting example. C02 is basically a 2 cube with one of its faces collapsed down to a vertex. And if you look at what this looks like geometrically, excuse me, you can see that this really looks like a 2 simplex. And that's basically what you would expect, because we started with a vertex and then we're just taking more and more cones on it. And that is exactly how we can construct simplices. So the more cones we take, starting from a vertex, we just get more things that are cubes. They're cubical sets, but they resemble simplices in a way that will be made precise very soon. So similarly, C03, isomorphic to C12, looks like a tetrahedron. C20, of course, just by definition, is the 2 cube. And here's a genuinely interesting example. So C21 is a cone on a 2 cube. So this basically looks like a pyramid with a sort of rectangular base. So we think of this as taking the 2 cube, taking a cylinder on that, so stretching it out to a 3 cube, and then collapsing one face down to a point. And this pretty much is the limit, the upper limit of my ability to draw these things. I don't think it would be very illuminating to try to draw a 4-dimensional object in LaTeX.
So I don't understand these indexing
way.
conventions. So I plus j is the dimension that it's a quotient from. But so if you have c, I, j, what's I and what's j?
So I is the dimension of the base that we start with. And then j is kind of the number of times that we've taken a cone. So like we start up here with a 0 simplex, and we do this we do this push out construction once, and we'd get, in that case, a 0-1 cone. So it's like every time we do this push out construction, every time we take a cylinder and then collapse one face to a point, that increases the second index by 1. Does that clear things up a bit?
Yeah, so could you talk us through an example then? So the isomorphism between C03 and C12.
Mm-hmm. C03 and C12. Right, so the reason why we get isomorphism essentially is because, for a more technical take on it, if you look at this push-out diagram that we have here, in the case where, right, so if we think about the construction of C01 from this push-out diagram, we would start with C00 in the top left corner here. So then that would just be box 0, so the map at the top would be an isomorphism. So then the push-out map along the bottom would be an isomorphism. So C01 would just be, in that case, box 1 tensor box 0, which would just be box 1. And then that isomorphism just sort of carries through to all the rest of them, so that we always have C0n isomorphic to C1 n minus 1. But that doesn't happen for any higher dimensions of the base, like C2, 0 and C2, 1 are not isomorphic to any other cones.
Got it. That's helpful. Thanks.
Okay. Anything else I can clarify? All right. Let's move on then. So we denote C0n by Qn, and that. So we saw that the cubes of the form C0n all basically looked like simplices, and in fact they define a co-simplicial object in the category of cubical sets. So we have this table then here which shows how every simplicial structure map this cosimplicial object, is induced by some map between the standard cubes, which then descends to a map between the quotients. So the simplicial faces are induced by the cubical face maps, and then the simplicial degeneracies are actually mostly induced by connections, as Chris discussed in his talk on Monday. So that shows why we really need connections in our box category in order to do this, because if we didn't have them, we wouldn't get this cosimplicial object. And so we can left-con extend this to get a functor Q from simplicial sets to cubical sets, which essentially takes a simplicial set and constructs a cubical set by thinking of the simplices in that simplicial set as cubes that have had certain faces quotiented down to degenerate faces. And Q has a right adjoint, which we denote by integral. And so the n simplices of integral x are just maps from Qn into x. And as I previously mentioned, and as Chris discussed in his talk on Monday, this coincides with the straightening-unstraightening adjunction if we think of simplicial sets as the slice category over delta 0, and cubical sets as the functor category from the terminal category to cubical sets. Right, so our approach then, our strategy, is going to be to show that this adjunction is a quill and equivalence, Q and integral, and use that to prove that triangulation and its right adjoint form a quill and equivalence. So first thing we would need to establish then is that the adjunction is a quill and adjunction, Q and integral, and that's really not hard to show. So what we need to show is that, well, Q preserves monomorphisms, and so that's fairly clear. Again, we can just check it on boundary inclusions because we're dealing with the left adjoint, and it's easy to see it sends those to monomorphisms. And to show that, well, we'd also need to show that Q sends inner horn fillings to trivial cofibrations, because we are looking at a quill and adjunction between the Joyal and cubical Joyal model structures. And that, again, is not hard to do. So if you take Q of an inner horn inclusion, you can show that what you get is a push out of an inner open box inclusion. Right, and so then the next thing we'd want to show here, to show that this is a quill and equivalence, is that the left adjoint Q preserves and reflects weak equivalences. So to do that, well, we have a brief sketch of a proof here. So Q and T both preserve weak equivalences because they're left quillen functors, and all objects in these model structures are cofibrant. And what we can do then is we can define a natural weak equivalence from this composite Q followed by T to the identity in simplicial sets. And so what this shows is that Q reflects weak equivalences. So if we have a map like this x to y, where Qx to Qy is a weak equivalence, so x to y is a map of simplicial sets, then T will preserve that weak equivalence. So the top map in this commuting diagram here will be a weak equivalence. Then x to y will also be 1 by 2 out of 3. Right, so then what we'd want to do is show that the co-unit of this adjunction at a fibrant object, so at a cubical quasi-category, is a weak equivalence. And we can show actually that it is a trivial cofibration. So in Chris's paper with Zach Lindsay and Liangzi Wang, which previously studied this adjunction Q and integral, They show that the co-unit is a monomorphism, and basically for cubical set x, q integral x is the subcomplex of x, whose cubes are those which factor through the quotient map from box n to qn. So we can think of this as sort of like the maximal simplicial set, which is contained in Q, thinking of this adjunction as a co-reflective inclusion of simplicial sets into cubical sets. And so what we do then is we look at this co-unit, which is an inclusion of this subcomplex, and we factor that as a series of subcomplex inclusions of these subcomplexes xm. And the way we define these subcomplexes basically is that the non-degenerate cubes of each of these subcomplexes xm are those cubes which factor through some cone on a base of dimension less than or equal to m. So to be precise, they factor through c m prime n prime for some m prime less than or equal to n. And this is pretty much the point where the proof in the paper starts to get very detailed and very technical. And this is where the 10 pages of combinatorics that Chris mentioned on Monday come into it. So unfortunately, I don't think I can get into any more detail about how we show that each of these subcomplex inclusions is a trivial cofibration, but basically what it amounts to is showing that each of them is a transfinite composite of inner open box fillings. And yeah, there's a lot of combinatorics of cubes that come into it, or yeah, cubes and cones in cubical sets that comes into it here. But right, so where do we go from there? Oh, sorry, I meant to actually take this slide out on the grounds that it was too technical, but I guess it's here anyway. So we factor each of these inclusions. So basically, we factor each of these inclusions further as another series of subcomplex inclusions, where we sort of, starting with the cones on a base of dimension m-1, we then add all the cones on a base of dimension m in order of increasing degree. So we would do certain push-outs of inner open box inclusions to add like just the m cubes, then the cones on m cubes, and then the cones on m cubes, and so on. Yeah, so I won't get into too much detail about that, but there is a very detailed construction of that in the paper. Right, so then once we've shown that Q and integral form equivalence, how do we know from that that T and its right adjoint U form equivalence? Well, it basically comes for free from stuff that we've already done. So you recall we had that natural weak equivalence from Q followed by T to the identity. So when we go to the homotopy category of simplicial sets, like the induced adjunctions between the homotopy categories of simplicial and cubical sets, that natural weak equivalence will become a natural isomorphism from the composite of the two derived functors of Q and T to the identity. So then we know that the derived functor of Q is an equivalence of categories, hence the same is true of T, because it's, I mean, what this shows is that it's they're inverses as equivalences of categories. And that is everything I had there. So we'll make a slide so you're not just staring at a blank screen.
All right. Thank you very much. So please join me in thanking Brendan for this great talk. Okay, and we have a bit of time for questions. And I'll just add, as part of the applause maybe, that Morgan had to leave only 3 minutes earlier, but she said thanks for the talk, Brendan. Yeah, so floor is open for questions.
I think this is all very fascinating. I'm very glad that you guys have done this. One
Thank
question
you.
I have, one advantage of quasi-categories is that every representable simplicial set is a fibrant object. I suppose that isn't the case here. Now, maybe that's not a problem. That's not true for Khan complexes. But have you run into that as a problem, or is it not something to worry about?
It hasn't caused us any problems so far. It is an interesting thing to point out, though, that is one of the ways in which the model structure we've constructed here is not quite as nice as the Joyal model structure, in that the representables for dimension 2 and higher are not fibrant.
So this is not a question I necessarily like to get, so I almost feel bad for asking it, but I am very curious. What do you think are the benefits of the cubical model over existing models of infinity one categories?
Well, one of the advantages of it is the cubical mapping spaces, right? The Joyal have to work with the left and the right mapping spaces, and perhaps the definition is a bit more awkward than we might like it to be. Whereas here, the definition of the cubical mapping spaces is very nice and easy to work with, and we just have one symmetric concept of the cubical mapping spaces. And we're hoping that the proof of the fundamental theorem that we get using that will be very nice and intuitive to construct. Maybe that's putting things a bit strongly, but that construction is one of the main benefits and advantages of it.
Yeah, that's neat. Do you think it might also help with type theoretic descriptions of infinity one categories? Since we seem to be good at doing things with cubes.
It's entirely possible. I'm not quite as familiar with the type theoretic side of things myself, so I'm not sure what I can say of any real substance about that myself. Yeah, I don't know. Chris, did you have any thoughts on that, on the applications of this to type theory, if any?
I personally wonder. So the thing about cubical type theory to me is that remember Tim's talk. Like Tim talked about characterizing cube categories in terms of substructural logics, and the thing about logics is that you really want structural, not substructural. So one thing that logicians deeply care about is the ability to repeat variables and permute variables. And so symmetries and diagonals, usually when I talk to the logic crowd, they don't even realize that you can consider a cube category that doesn't have those. Whereas connections are this weird thing that you may or may not add, right? And then for a homotopy theorist, I think it's the other way around, where symmetries and permuting things is a nightmare. And like when you talk about symmetric simplicial sets or symmetric cubical sets, like if you look at people that like what kind of acknowledgements people write in their papers, usually when they study symmetric simplicial sets or symmetric cubical sets, the acknowledgements for personal support are much longer in these papers. No, I just totally made it up, but there's usually far more struggle with this, and so there's this disconnect between, I think, logic and homotopy theory, and that's okay. I think so. This is something that's really supposed to work for homotopy theoretic applications, less so type theoretic applications. Although, when it comes to directed type theories, I think there's another expert in the room. So maybe Emily can comment. I'll add one more thing, maybe, to the earlier question about possible applications. So there are many cases in which we can enrich something over cubical sets rather than simplicial sets, right? And so I would expect that things enriched in our model structure, considering that maybe a convenient model for infinity two categories, where right, so enriching over that, that can be an infinity two category, and often you like when you want to work in enrichment in quasi categories, you then need to triangulate it. But when you triangulate things, you lose fibrancy. So I would expect that there are some nice examples, maybe in algebraic geometry or maybe in symplectic geometry, of things that are naturally cubical, and you can build a Fibrant cubical enrichment in our sense. And then if you were to triangulate, you lose fibrancy, and so the infinity two categorical methods, simplicial infinity two categorical methods may not work quite as well.
Okay, can you give an example of what you mean by having to triangulate?
Oh, I'm just saying, like, if you, again, it's hard to come up with an example on the top of my head, but like often, like even thinking about the homotopic coherent net, right? Like the mapping space there is a cube naturally, and then you triangulate it and you get something, something that's simplicial, right? Like you artificially made it this way. So now, I don't want to see something, yeah.
Like in algebraic geometry, I have A1 cross A1.
Yeah,
but I don't want to really glue two A2s along the diagonal.
Yeah, so I can imagine that like there are some things in algebraic geometry where like those cubical shapes are quite natural, and and you can build some sort of enrichment. I'm not qualified to talk about it this way, but definitely there must be examples of that. So I would imagine that this framework applies to that situation. And again, I would love to like talk. If Ezra was here, probably he would be the right person to ask.
Well, now that you've conveyed your meaning, I actually could give you an example about the infinity one kind of enrichment in this cubical Joyal structure, but just for some ordinary cubical. Oh, but the connections might be a little trickier. Oh, connections probably even by product or something, or I don't know. Well, so I mean, one problem that happens in algebraic geometry, let's say you want a co-simplicial, you want to say what is the algebraic version of the topological n simplex? And some of the best approximation that you can imagine would be just like AN, right? Because you can't like carve out inside by inequalities, just simplex. But then you don't have, so you can try to use, just take the definition of delta n, delete all the inequalities from it. You'll still get a co-simplicial object, but it'll no longer be true that this sort of geometric realization functor preserves products because, well, if you take delta 1 cross delta 1, that's going to get sent, well, you'd like it to be sent to A1 cross A1, but actually delta 1 cross delta 1 is like two simplices glued along the diagonal. And so you actually get out is two copies of A2 glued along like the line x equals y, right? And that's not the same as A2. But you could write down a monoidal functor from cube category that just sends brackets 1 to the n to AN, and that would be fine. Does that make sense?
Yeah, because exactly you have the faces. Yeah, I think that works.
I don't know what you do with connections if that poses any challenge. If you can use min, if you have multiplication, can you use that for min connections? I don't know.
And the other option would be to remove connections and do this two-step construction that we discussed earlier, right? Like for Q, freely add connections, and then I suspect that you can play the same game and get an equivalent model structure without connections. So it's Yeah. Okay.
Well, if I might,
Yeah.
oh, sorry, go on.
Go ahead. Go ahead.
I was going to ask a question on a different topic, but I don't want to interrupt the flow.
Go for it.
Okay. So you've got these Quillen equivalences between the cubical Joyal model structure on cubical sets and the Joyal model structure on simplicial sets.
Mm-hmm.
Do you have a direct Quillen equivalence between, the Joyal model structure on marked cubical sets and the, let's call it a Joyal model structure on marked simplicial sets?
Mm. Oh, we haven't constructed anything like that so far, at least.
Okay. So my second related question to that would be maybe that would elucidate the marked straightening over a point in the same way that this Q and integral you did for the unmarked straightening over a point.
That is a very interesting idea. That that might be worth looking into.
I mean, maybe just like when you have triangulation, you can you can kind of quite clearly mark it, right?
Mm-hmm.
And then you have the square of like the triangulations and forgetting marking and triangulations that forms a commutative square. And we proved that 3 out of those are weak equivalences, or Quillen equivalences. So but I've left Quillen equivalences. So even we don't elaborate on it, but it kind of. But for straightening, we don't have such a nice,
It would certainly be nice if this could help with the marked straightening over a point, or marked straightening in general.
Yeah, so we also thought of analogs of the Cartesian model structure, but I think, I don't think we don't want to do an analog of that. Like we probably would rather do 2 kinds of markings instead.
Sure.
Just because, thinking as you're generating, all markings and indexing overall count complexes is all right. Anyone else?
This isn't really a question. I don't know if this is a good thing to say, but I think that your notation CMN is backwards. It should be CNN, or the indices. When I saw them, my guess was exactly what you wrote, except M and N were swapped. And I think maybe in some other context, but it's like you just apply the the coning operation some number of times to some object, which is box M.
That's
box,
exactly it. Yes.
Second coordinate, right?
Mm-hmm.
So it's just, if you call it coning C, it's like C, C of box something, and so it makes sense to keep the indices in the same order. And also, when you build the cube, you actually the cone coordinate is actually on the left, right? If I understood your push out correctly, and so the coordinates actually they come before.
It is, yes. I've gone too far. Oh no, not yet. Yeah, yes, you're right. It is. We do tensor on the left of box 1 to get the direction in which we take the cylinder and then quotient to get a cone.
That might not be helpful.
That's a fair point. I mean, there wasn't really a deep theory behind our particular choice of that ordering of the indices. So a different order might well be more intuitive.
Also, I had a question that I was reminded of when you flipped through the slides. I might have just missed it, but did you tell us what the map from TQ to the identity was? Like it's.
No, I didn't get into the. I didn't explain what the natural equivalence actually is. It's constructed in detail in the paper, but I didn't really have like kind of a nice intuitive way to describe it. It's sort of a technical construction. I guess, I guess one way to think of it would be if you take a simplicial set, apply Q to get a cubical set, and then triangulate again. That should sort of amount to taking those, like the simplices of your initial simplicial set, and then sort of breaking them up into multiple simplices, and then the natural weak equivalence kind of collapses all of those back down to the original simplices that you started with. I know that's very vague and loose, but in the actual paper, it's described. It's described by a construction that involves sort of an. What's that, sorry?
It's sort of like subdivision, right? And then a map from subdivision back to the.
It is, yeah. That's how I would think of it, as a kind of subdivision. And the actual detailed construction involves these simplicial structure maps and how they're induced by maps between the cubes that induce maps on the quotients. Yeah, so there's not much more I can really say about that without getting very technical about it.
Sure. Thanks. I just wasn't sure if I missed it when you said something.
Oh yeah, no problem. Well, it was a good question.
All right. Any more questions? In this case, I suggest we thank Brandon again for both talks. Okay.